You look at a 50-kilometer sea bridge and see steel and pavement. You are looking at maybe 20% of the actual engineering. The other 80% sits underwater. Cage is the height of a 14-story building lowered into holes 100 meters deep in mud that collapses on itself if left alone for minutes. Keep watching to the end for the moment workers drive wedges into a finished pile head and break the top off. A bridge does not begin where the deck sits. It begins tens of meters below, in a place nobody watching will ever see. The Hong Kong-Zhuhai Macao Bridge stretches roughly 50 kilometers across open water, and every meter of that deck rests on foundations drilled through mud, sand, and rock beneath the sea. Barges float rigs into position. Rebar cages the height of a 5-story building are welded on deck, then swung by crane down into casings that already run past the waterline. You look at the finished bridge and see steel and pavement. You are looking at maybe 20% of the actual engineering. And the machines that build this hidden foundation are absurdly serious pieces of hardware. Rotary drilling rigs the size of small buildings, mounted on crawler tracks, with masts tall enough to swing a Kelly bar that runs 40, 60, sometimes 90 meters straight down into the earth. Each rig weighs hundreds of tons. Each one is designed for a job most people never think about. Making a hole in the ground that stays open long enough to become a concrete column. Try digging a hole in wet sand at the beach and watch what happens in 10 seconds. Now scale that to 3 meters wide and 100 meters deep, in mud, underwater. Every rig on a site like this works against gravity and pressure, one bucket at a time, sometimes for weeks per pile. The bridge above will stand on what these machines leave behind. Invisible, permanent, and completely dependent on what happens in the next few hundred meters below. Some jobs need normal hardware. Others need a hammer the size of a house. For the Hong Kong-Zhuhai Macao project, engineers built the largest vibratory pile driver ever assembled. 8 units linked as one, gripping a steel caisson 22 meters wide. Watching that thing lower a caisson into the seabed is when you realize this is not construction anymore. This is planetary-scale plumbing. But before any big rig shows up, a much smaller one has already done the work that decides everything. A small survey drill sinks a borehole at each planned pier location and pulls up cores of what is actually down there. Silt, clay, sand, weathered rock, solid bedrock. The standard penetration test drops a weighted hammer onto a sampler and counts blows per foot of penetration. Soft ground gives up in a handful of blows. Dense sand or fractured rock takes 50 or more. That number is what the whole bridge above will be sized around, and getting it wrong means designing a pile that either stops short of good ground or drives past it into money. Every step of the survey feeds directly into what happens next. Test pits open the topsoil to check bearing layers. Steel casings are pre-fitted at every planned pier. Onshore rebar cages get fabricated in workshops so the geometry matches survey coordinates within millimeters before anything goes into water. A viaduct running through a live urban river has zero tolerance for surprises underneath, and the workshop is where those surprises get eliminated before they become expensive. At each pier location, the sequence tightens. Fabricate the rebar cage, excavate the shaft, install the cage, test the concrete, pour. The cage itself is a cylinder of longitudinal bars and spiral hoops assembled by hand and inspected before being lifted vertical. Slump tests on the concrete happen right at the truck, because concrete that fails the test at 5 p.m. does not get poured at 5:15. Nobody at a foundation site wants to hear the phrase "wrong mix." At a port site, the layout goes another dimension. Barges carrying drilling rigs anchor above each planned pier position, concrete batches on shore. Boom pumps deliver concrete out along the water surface to where it needs to land. Every meter between the batch plant and the pile is one more meter where the mix could segregate or start setting. On land, you time the pour in minutes. Offshore, you time it in nervous minutes. GPS marks the pile center line for every drill hit. Even the rebar fabrication happens on hanging platforms suspended above the water. Crews weld cage sections during low tide because that is the only window when the river gives them elbow room. Miss the tide, and the next chance is 12 hours later. When the location decides the schedule stops being a suggestion. Getting a 100-ton rig onto a pontoon in the middle of a river is not a trivial delivery problem. The mast and hydraulic lines fold down for transport, so the rig fits on a normal trailer. Quick mount systems raise the mast back into working position in hours instead of days. Long crawler tracks give the machine stability on the barge deck even when the water underneath shifts. The rotary head at the top of the mast is where the real power lives. Hundreds of kilonewton meters of torque driving a Kelly bar that reaches 90 meters or more. The whole thing runs off a diesel engine tuned for continuous heavy load. When it arrives at the platform, it does not look like a rig that folded up an hour ago. It looks like a small factory bolted to a barge. The St. Croix crossing used a precast cofferdam system with a concrete deck as the work platform. 4 large circular openings guided the casings straight down. Casings passed through 25 feet of water, up to 87 feet of muck, sand, and gravel, and into bedrock below, all before drilling even started. Now scale the same idea up until it stops looking like a construction site and starts looking like a small port. For the Macao Bridge, giant tower foundations were prefabricated on shore as steel and rebar caissons, then floated out to the strait. Cranes on barges swung components into position. Welders climbed, scaffolds meters above the water. Every visible element on the surface is a hint of the drilling and pouring already finished underneath. By spring, the same site had grown into something you cannot fit inside a frame. Massive cylindrical foundations were being lowered into the water. Excavation pits on land held rebar mats and formwork the size of small buildings, all pre-assembled so that when they reached the water, they could be lowered in one operation. Drilling rigs worked under floodlights at night. The scale is what breaks people watching this footage. Aerial shots show maybe 15 barges around a single tower base, and you realize each of them is doing a different job. One drilling, one placing rebar, one pouring concrete, one moving supplies. No barge sits idle. The guide frame keeps every casing straight to within tight tolerances, because a casing off vertical by a few degrees means the hole beneath it curves off center by meters at final depth. Survey teams on rigid platforms track every millimeter. Component after component gets moved by crane from shore to platform, then lowered, welded, and locked into place. This is what happens when a bridge over a strait becomes a construction project that runs 24 hours a day for years. At Winona, hollow steel casings 42 inches wide and 80 feet long get pounded to bedrock by a diesel hammer. Each pile takes about an hour. Time-lapse compresses that to 20 seconds. The hammer never gets bored. Here is where the actual drilling begins, and where the ground starts pushing back. A rotary rig lowers a drilling bucket at the end of a Kelly bar down the casing. The bucket rotates, cuts, fills with soil, closes at the base, then gets pulled all the way back up to be emptied on the surface. That is one cycle. To drill a 60-meter hole, the rig repeats that cycle dozens of times per pile, and every meter of depth adds time for the bucket to travel up and down. The operator watches torque gauges the whole time. A sudden spike means the bucket has hit dense sand or rock, and the tool needs changing. Modern rigs have automated monitoring, showing depth, verticality, and torque in real time. The operator holds a remote or works from an air-conditioned cabin, but the actual fight is happening 40 meters below where nobody can see. Every bucket brought up dripping mud is a small victory against a hole that would collapse on itself if left alone for even a few minutes. Some piles run 90 or 100 meters deep. That is a lot of small victories. Reverse circulation drilling uses fluid pressure to push cuttings up through the center of the drill string instead of hauling them out with a bucket. Continuous flow, no cycling, faster removal on the right ground. A casing rotator spins the steel casing itself into the ground as the drill works underneath. Two forces going the same direction, at the same time, without turning each other into scrap. A remote-controlled casing driver clamps around the casing and drives it downward under compressed air. No worker needs to stand next to it, which is the correct number of workers to be near a moving 30-ton clamp. At a river site, the sequence stacks. Jack-up barge in position. First pile driven. More piles added around it. Cofferdam walls built to enclose the group. Water pumped out to expose the pile heads. Rebar cage lowered. Formwork installed. Concrete poured. Each step depends on the previous one holding. Skip one, and the next one has no ground to stand on. At the Hong Kong Zhuhai Macao Bridge, some foundation elements are not piles in the normal sense. They are steel cylinders, 22 meters wide, 40 meters long, weighing around 450 metric tons each. 8 vibratory hammers linked together grip the top of each cylinder and shake it downward into the seabed with combined driving force of thousands of tons. The scale is comical until you realize this is the working method, not a demonstration. The hammer specs list eccentric moment in units of kilogram meter, and the numbers only make sense if you accept that a single foundation element for this bridge is larger than most residential buildings. Below the waterline, each cylinder is now the shell of what will eventually become a pier base. The concrete goes in after. The jack-up rises on its legs above the water, and suddenly the tide is somebody else's problem. From that stable deck, tubes and sheet piles get interlocked into a continuous wall. But a hole is only half the foundation. The other half is a steel skeleton nobody will ever see again. A rebar cage for a board pile starts as flat lengths of steel bent into spiral hoops on a bar bender. Workers assemble the cage lying horizontal on the ground. Spiral hoops slid onto vertical longitudinal bars, then tied at every intersection with wire. Every knot in that cage is a decision that concrete relies on for the next 50 years. A tall cage takes days of continuous manual work, and the geometry is what carries load from the deck above straight down into rock. An operator enters bar count, cage length, and diameter on an 8-inch color display. The machine feeds vertical bars, wraps the spiral around them, and welds each intersection as it goes. The controls fit on a screen the size of a laptop. The output fits on nothing smaller than a flatbed truck. Variable pitch means the spiral can tighten where the pile needs more confinement, at the top and bottom, and open up through the middle where the loads are lower. Automation removes most of the labor and most of the geometry error at the same time. At 2.5 meters wide, the cage is already enormous. The machine welds spiral wrap continuously along the full length. One machine, one operator, one cage that will end up 60 meters underground. Bars run down a conveyor with rollers under the operator's watch. Kick-off arms fire at the right moment to drop each finished piece into its bin. A shoreline built decades ago is still running in most fabrication yards today because there is no clever way to replace it. Cut, sort, stack, repeat until the day ends. The cage cannot exist without the length sorting that happened here first. Yearly output measured in millions of couplers and thousands of kilometers of sonic tubes. All of it eventually ends up in cages somewhere. The bridge you drive over depends on parts nobody outside this trade has ever heard of. The bar end glows orange under the forge, then gets pressed into a flat mushroom head with a serial number stamped on it. A bar with a head at each end anchors in tighter, congested cages where standard hooks would not fit. Now the interesting problem. A 148-foot cage does not exist as one piece. It gets fabricated in sections and connected at the site as each part is lowered. Threaded mechanical couplers screw onto the bar ends, joining sections into one continuous cage while the first part hangs from the crane. Workers tighten each coupler by hand with impact wrenches. 148 feet of cage. Every splice on that cage is the difference between one foundation and a lot of expensive scrap steel, which is roughly the height of a 14-story building, being assembled vertically in the open air over a hole. Sometimes the cage lands too high in the hole and standard hooks end up outside the concrete pour. The fix: cut the hooks off and thread field-installed T-head anchors onto the bar ends. A worker with an impact wrench turns a mistake into a correction in minutes. Every foundation crew has done this. Nobody puts it in the brochure. With the hole prepared and the cage in place, the next step is the one nobody outside this trade truly understands. You do not pour concrete into a shaft full of water. You displace the water with concrete from the bottom up. A tremie pipe reaches nearly to the base of the shaft before pouring starts. Concrete flowing out the bottom of the pipe pushes water and slurry upward and out. As the pour continues, more pipe sections get removed from the top, keeping the pipe's outlet buried in the fresh concrete. Break that rule and the water comes back into the mix. The animation shows it clean. Surveyor marks the position, rig drills with support, fluid, cage goes in, tremie pipe follows, plug placed at the bottom, concrete rises. Slurry displaces upward and out of the casing while concrete fills below. The cleanest version of a very messy real-world operation. Before any concrete leaves the truck, a probe called squid drops to the base of the shaft on the Kelly bar. Its penetrometers measure debris thickness in real time. Loose sediment at the bottom means the cleanout was not finished. Thermal wire cables run the full length of the cage. Data collectors connect to each cable and start logging temperatures roughly every 15 minutes after casting. Heat rises where concrete is thick and dips where something is wrong. Necks, bulges, and cage off-center, all readable from the temperature pattern the concrete leaves behind as it cures. Miss the cable installation window and the test option disappears with it. An embedded hydraulic cell pushes upward and downward simultaneously, letting engineers measure shaft capacity without needing a reaction frame at the surface. Installed before the pour. Instrumented once, buried forever. Days after the pour, the pile head still looks nothing like a foundation. It looks like a lump of contaminated concrete, because that is exactly what it is. During the tremie pour, impurities floated to the top and got trapped in the last meter or two of concrete. Every one of those upper meters has to come off. Workers cut a horizontal groove around the pile with a grinder, then drive wedges called ciria into vertical splits until the top breaks away as one piece. A jackhammer finishes the ragged edges, rebar that was already tied into the cage, sticking up above the design cut line, gets cleaned off and left exposed. That exposed rebar is what will bond into the pile cap above. The pile you designed sits below where the mess used to be. The mess above it? That was insurance the tremie process worked correctly. Tubes tied along the cage get filled with water after the pour. Transceiver probes drop to the base and scan upward with ultrasonic pulses. Delayed arrival times equal anomalies. Concrete becomes readable, one pulse at a time. With the piles cleaned and inspected, they finally get connected. A group of piles under one pier does not act as a group until the pile cap links them at the top. Cofferdams pump out the water. The pile heads sit, exposed with rebar sticking out, and workers weave a new rebar mat between them at the level of the cap. Longitudinal bars run in both directions. Vertical bars from every pile rise into the cap and lap with the new steel. Concrete pumps deliver the pour. What was 20 or 30 separate piles working alone becomes one monolithic base carrying the load of the pier column above. The pile cap is the handshake between the buried skeleton and the visible bridge. Once it cures, the cofferdam walls come out, water floods back, and the cap disappears under the surface. From here, the column rises above the water. The first part of the bridge anyone driving past will actually notice. For the Zhuhai Bridge in Serbia, the central pier sits on the foundation of a bridge destroyed in 1999. Sheet pile enclosure and jet grouting sealed the perimeter. Divers excavated the riverbed to 14 meters below the water surface, then repaired the old foundation. The new pier rose from what the old one left behind. A bridge foundation is the one part of a project that lasts longer than the bridge sitting on it. Wait for it. After all that mud and slurry, the payoff climbs into the sky. A 113-meter pylon curves upward from a foundation that started as bored piles under the river. Stay cables reach down to a 200-meter main span, 6 lanes of traffic, pedestrian walkways on both sides. Everything you can see above the water rests on everything nobody ever saw below it. By 2021, the Macao Bridge had grown into something the drone shots barely hold in one frame. The towers reached full height, red against a strait full of ferry traffic. Cables started running from tower tops down toward the deck line. Workers crossed high-angle scaffolds hundreds of meters above water, tightening cable anchors that would eventually hold the entire suspension load. Below, workers still poured concrete into rebar mats for the approach spans on land, and pavers laid asphalt on the finished lanes running toward the water. Every element visible in these frames traces back to the drilling that started years earlier. The towers you see standing 300 meters tall are only there because someone drilled a hole roughly the same depth into the seabed beneath them. Above and below balance each other on this kind of structure. Take away either half and the other stops making sense. A few months later, prefabricated deck sections started arriving by barge. Floating cranes hoisted them one by one to the height of the main cables and hung them from suspender ropes. Workers walked out onto each new section as it was locked into place. The deck grew span by span across open water, each addition transferring load into the cable system. The engineers who drilled the tower foundations were long finished with the job. The deck above just kept getting heavier. By late 2021, the deck ran continuously between the towers. Asphalt pavers laid the surface layer. Workers bolted structural connections and welded expansion elements. Cargo ships passed underneath the completed span, some of them larger than the bridge's own construction barges from years earlier. The strait now had a permanent crossing, the whole visible bridge. Every meter of deck, every cable, every tower, rests on foundations most people watching this footage will never think about. The Governor Mario M. Cuomo Bridge carries over 138,000 vehicles a day across the Hudson. Modular expansion joints handle up to 1.4 meters of longitudinal movement. Everything you feel driving over it, every bump, every seam, traces back through the deck to piles somewhere under the water. Every bridge you have ever crossed is standing on work that was finished before the deck existed. The concrete tower, the steel cable, the asphalt lane. All of it traces down to a hole drilled through mud and rock while nobody was watching. 60 meters of pile per week is a good project. And after all that, the pile disappears under a river forever. The bridge above is only the reward for what the drilling rig already delivered. Here's what people rarely notice. The engineer who drilled it will never see that pile again. Once cured, it becomes permanent, invisible infrastructure. Any defect stays. Correction has to happen before the pour. How deep do you think the foundations run under a bridge in your own city? 10 meters? 100? Share your guess in the comments. Subscribe for the next one. See you then. Take care.